In our previous lessons, we were looking at the relationship between temperature, activation energy, and K. We're going to see this mathematically played out in what's called the arrhenius equation. And our learning objective for this lesson is to utilize the arrhenius equation to determine the rate constant, the temperature, or the activation energy of a reaction. And we're going to see the way that they interplay and relate off of each other. This is the arrhenius equation. And let's look at the various components of the equation. Talk about each one of them. Many of them we have seen before. This is obviously the rate constant, K. And we'll be able to see how the rate constant changes depending upon the activation energy or the temperature. We know that E sub A stands for the activation energy. This is reported and utilized either in kilojoules per mole or joules per mole. We'll see as we proceed on. We've got to make sure our units cancel properly. R is the ideal gas constant. Now the ideal gas constant that we're going to want to use has units of joules per mole. Notice that I said this was kilojoules. Now we cannot put these both in there with these same units. We either must have them both in joules, so we could convert this one to joules, or we could have them both in kilojoules and we can convert this one to kilojoules. But those units are going to have to cancel with each other in order for this to work properly. It is very common for students to miss that up. They just plug numbers in and not think about their units. So I'm talking about your units for a reason. It's the easiest way to make a mistake here. Okay, if we're talking about units, what will the units of temperature have to be in? Well, as a hint, look over there at the gas constant. What's the unit of temperature in it? Well, it's Kelvin. So you better put your temperature in Kelvin or this equation will not work. So we've got our K, our activation energy, our R, our T. This E has the exponent, the inverse of the natural log. Okay, so that's what that is referring to. What about the A? The A here is called the frequency factor. And it is a constant for the reaction system. It takes into account other avenues, other things that are unique to that reaction, like how do the molecules have to be oriented when they collide. We'll talk more about this frequency factor later in our lesson. Okay, so we have this expression. What we want to do first is just think about how this plays out with what we already know is occurring on the molecular level. So over here I've got some conditions. Let's think about changing activation energy. As activation energy gets larger and larger, and we're looking at this portion of the equation, we are raising it to a more and more negative value, E to a larger and larger negative number. Well, how does that affect the value of K? Well, if you're raising it to a larger negative number, it becomes a smaller and smaller fraction. So K is going to go down. Now, does that make sense with what we know about activation energy? Well, let's think about the mountain size. If it's a really, really high mountain, is it going to be a slower reaction? There's going to be a few molecules that can get over that. So is it going to be a slower reaction, so you can expect a smaller K? All right, let's think about temperature's role. Now, where does temperature in this equation? Temperature is right here in the denominator. As temperature goes up, we are dividing by a larger and larger number. So it's going to decrease the size of this portion of the number. So it's to a smaller negative number. If it's to a smaller negative number, then K is going to become bigger and bigger. Well, let's think about how that makes sense with what we know about what's happening on the molecular level. We've got a certain mountain to climb. As temperature's going up, we've got more molecules that have enough energy to get over that mountain. If there's more molecules that have enough energy to get over that mountain, wouldn't the reaction take place at a faster speed, therefore have a larger K value? Now, we're going to do some manipulations. What our goal in the end is going to be is to have a slope-intercept form of a line. So we'll just take the natural log of both sides. Natural log of both sides, we're taking the natural log of a product here. Okay, so we have the natural log of this product two things. So we're going to have the natural log of a plus the natural log of e to the negative e sub a over r. The natural logs will cancel, and that will leave me with a negative e sub a over rt. Let's do a little rearranging. Now what I've not just done rearranging, but I've done regrouping. You kind of want to look at what's happening. I have moved this over here to the left side, but I've also grouped things together a little bit differently. The reason I've done that is so that it is in the form y equals mx plus b. So kind of lined it up underneath there so you know what each thing is. So what will a plot of natural log of k, that's my y, versus 1 over t, that's my x. It's going to definitely give you a straight line. Well, what is the slope going to be equal to? Well, that's this whole portion here. That's m. That's the slope. Negative e sub a over r. So you could graphically determine the activation energy by running this experiment at various temperatures, getting multiple k's, and obtaining an activation energy from the graph. Here is an example. If you're given k's and temperatures, you would need to first take those k's and take the natural log of them. You would take those temperatures and take 1 over those temperatures. Then plot out natural log of k along the y-axis, 1 over t along the x-axis, and then you can take the best straight line through those points. Once you have the best straight line through those points, you could take two values off of that line. You could do a change in y over a change of x and have the slope. Once you have the slope, we know that the slope is equal to negative e sub a over r, and you could then obtain the activation energy. Now, how many points does it take to make a straight line? Only 2. So we're going to do a little derivation. Actually, I'm just going to kind of skip through the derivation but tell you how you get to there. If you take this Arrhenius equation, and this is the slope-intercept form of that equation, and you take it for 2 data points. Let's take it for a K2 with a T2, and then do the same thing, a natural log of K1 with a 1 over T1. Take those 2 equations and subtract them. Okay, you can derive the 2-point equation for the Arrhenius equation. And then you've got a relationship between 2 temperatures, 2 rate constants, and it could be a way to obtain an activation energy. But basically in this equation, you've got 1, 2, 3, 4, 5 variables. And if you know 4 of them, you can solve for the 5th. And that's very often asked of you within problems in this section. So I've given you one here. I've got a reaction in which I've given you the activation energy. So this is E sub A. I've told you the rate constant K at 35 degrees Celsius. So let's call this K1 and let's call this T1. And we want to know the K, and we'll say it's K2, and we'll call this T2. Now remember, you've got to have your temperatures in Kelvin. So let's figure out T1 in Kelvin. It would be 273 plus 35. And T2 would be 273 plus 0. That's obviously 273 Kelvin. And let's see, that's 80308. And I don't quite have room, but I'm going to try to sneak a K in there. Nope, can't get the K in. But you know that that little blob right there is a K. All right, so those are the temperatures. Now we're ready to put everything we know into our Arrhenius equation. Now I'm going to call K, I called K2 what I don't know. And I like having it up on the top. It really doesn't matter which one you put on top and which one you put on bottom, as long as you're consistent that whatever K2 is, you put it in the spot where T2 needs to go. K1's value is 1.35 times 10 to the minus 4 seconds to the minus 1. And that is going to be equal to negative E sub A over R. Now here's where you got to watch the energy units. I'm going to go ahead and convert my kilojoules per mole to joules per mole. That would be 1,000 more. So 102,000 joules per mole is my activation energy. My R is 8.314 joules per mole times Kelvin, both of those in the denominator. Okay, and then we have 1 over T2. Now I've assigned T2 as the 273 minus 1 over T1, which was 308. And those are both in Kelvin. So we look for our units and see how they cancel. Joules are going to cancel. Moles are going to cancel. And now this Kelvin is in the denominator of the denominator. And so the kelvins will cancel each other as well, because if you're in the denominator of the denominator, that takes a reciprocal and puts it up in the numerator. And so my kelvins will cancel. And I'm left with no unit, and that is what you should have at this point. Okay, so let's do a little work here. When I combine, and you'll want to do all of this, when you do the mathematics of this entire left side, you will get a negative 5.107. A very common mistake for students is they lose this minus sign. Don't do that. And that is going to be equal to the natural log of K2 over 1.35 times 10 to the minus 4 seconds to the minus 1. Now I want to get into that K2. How do I do that? I take E to both sides. When I take E on this side, it cancels those out, and I'm left with K2 divided by 1.35 times 10 to the minus 4 seconds to the minus 1. And when I take E2, a negative 5.107, I have 0.00606. Now I'm ready to solve for K2 by multiplying both sides by 1.35 times 10 to the minus 4. And that will give me K2 is equal to 0.00606 times 1.35 times 10 to the minus 4 seconds to the minus 1. And that will give me a K2 value of 8.18 times 10 to the minus 7 seconds to the minus 1. Let's think if this makes sense. What did we do to our temperature? We went from 35, where we knew a K, down to 0. So we dropped the temperature. If we drop the temperature, the rate should decrease, and it does so by having a smaller K. Is our K smaller? Well, certainly it is. So at least we know that this number makes sense for the work that we have done. Okay, so with our arrhenius equation, we see the relationship between temperature, activation energy, and K. But we need to mention a little bit about that frequency factor A that comes out of that arrhenius equation. That quantity frequency factor is going to be dependent upon a couple of things. Number one, it takes into account the collision frequency. Therefore, it's called the frequency factor. And with that, you take into account the state of matter, for example. If something is a gas state, the molecules are free to move, and they move very, very rapidly, so they can collide with each other, but there's great distances between them. But if they're in a liquid state and they can still move pretty quickly, but they are much, much closer together, they'll collide more frequency, so that takes into account the state. If it's a solid, they don't move very freely and they can't collide very frequently, so that would have a different frequency factor. It also takes into account the orientation of the molecules, because sometimes one collision, even if it has a lot of energy, won't result in a reaction. And we see that here in the top image. In the top image, if they were to collide, maybe no reaction would occur. But if they collided and the green ran into the green, then there could be a reaction. So if there is an orientation necessary to have a collision, that'll come out into that arrhenius equation. So In conclusion with this lesson and our learning objective here, we see that there's a mathematical relationship between temperature, activation energy, and the rate constant K. We saw how to graph it out in order to obtain a linear relationship, and how to plug in the 2-point value equation with the K1, T1, K2, T2, how to be able to obtain an unknown out of that equation. And lastly, we see how the frequency factor A plays a role in the rates of reactions as well.